Hello students, welcome to Digital Signal Processing course. So this is our week 5 lecture. So in week 5, we are going to study about the remaining part of analog to digital conversion techniques. So in our previous lecture, we started about the analog to signal conversion processes. So we have completed discussing about the first process, which is the sampling. Now, in this lecture, we are going to discuss about the remaining process, the remaining two steps in this conversion techniques, which are quantization and encoding. So, firstly, let's discuss about the sampling theorem in briefly. So, in sampling theorem, in sampling theorem, we have already studied about sampling theorem in analog communication or basic communication course. So, in case of sampling theorem, uh, uh, what has been uh, what has been given, or what theory has been given in this theorem, that if a signal is if a signal contain a frequency of f, uh, say for example, this is one analog signal, so it has a frequency f1. Okay, so this is the frequency f1. Now, say for example, this is the maximum frequency of this signal. So this is the maximum frequency of this signal. So now, say for example, this is f max is equal to f1. So f max is equal to f1, and this is the maximum frequency of this analog signal. Now, when performing sampling, we have to choose one sampling frequency. Now, in the sampling theorem, a relation between f max and fs has been given. That relation is that the sampling frequency should be greater than or at least equal to twice of f maximum. Now, why we need to follow this condition? If we do not follow this condition, then the reconstruction of the signal at the receiving end will not be successful. So for the successful reconstruction of the signal at the receiving end, we must ensure this condition here. Now, one scientist known as Nyquist he has given us a theorem similar to this, and he has explained that the sampling frequency should be equal to at least twice of the maximum frequency of that signal. So this value is known as the Nyquist rate. Nyquist rate. Okay. So if the maximum frequency of a signal is, say, for example, 3000 hertz, then the sampling frequency fs, or the Nyquist rate, which is denoted by Fn, should be equal to 6000 hertz. Okay. Now this is the sampling frequency fs. So fs should be greater than twice of f maximum. Okay. So this is done to avoid the reconstruction problem, which is known as aliasing. Okay. So if we discuss about this aliasing problem or reconstruction problem. Then we can say that let's suppose that any signal can be represented as a sum of sinusoids of different amplitudes, frequencies, and phases. That is, XA is equal to summation of AI cos 2 pi FIT plus theta I. So here the value of I varies from 1 to n. So the signal XA can be referred as the summation of different amplitudes and frequencies. So we can write this signal like this. So X A T can be written like A1 cos 2 pi F1 T plus theta 1 plus A2 cos 2 pi F2 T plus theta 2 plus A3 cos 2 pi F3T plus theta 3 and so on. So a signal can have different frequency components. So different frequency components may have different values. So we have to take the value of the maximum frequency, which is termed as F maximum. So say, for example, this frequency is 2 hertz, this is 6 hertz, this is 10 hertz. So what is our maximum frequency of the signal XT? 10 hertz. So if maximum should be equal to 10 hertz, now for the sampling frequency should be equal to 20 hertz or greater than 20 hertz. Yeah. So where n denotes the number of frequency components. All signals such as speech and video lend themselves to such a representation over any short time segment. The amplitudes, frequencies, and phases usually change slowly with time from one time segment to another. However, suppose that the frequencies do not exceed some known frequency, say F maximum. For example, F maximum is equal to 3000 Hz for the class of speech signals, and F maximum is equal to 5 megahertz for television signals. So for television signals, the maximum frequency range is 5 megahertz, and for speech signal, the maximum range of frequency is 3000 Hz. You have to remember these values for future. Since the maximum frequency may vary slightly from different realizations among signals of any given class, it may vary slightly from speaker to speaker. We may wish to ensure that if maximum does not exceed some predetermined value by passing the analog signal through a filter that severely attenuates frequency components above F maximum. Thus, we are certain that no signal in the class contains frequency components significant amplitude or power above F maximum. In practice, such filtering is commonly used prior to sampling. So in case of using filter, we have to consider the frequency of the filter, which should not be less than F maximum. Now, from our knowledge of F maximum, we can select the appropriate sampling rate. We know that the highest frequency in an analog signal that can be unambiguously reconstructed when the signal is sampled at a rate of Fs is equal to 1 by T, and which is Fs by 2. So any frequency above Fs by 2 or below minus Fs by 2 results in samples that are identical with a corresponding frequency in the range minus Fs by 2 to Fs by 2. To avoid the ambiguities resulting from aliasing, we must select the sampling rate to be sufficiently high. That is, we must select Fs by 2 to be greater than F maximum. Thus, to avoid the problem of aliasing, fs is selected so that fs should be greater than 2 of maximum. Now, the sampling theorem. So the sampling theorem says that if the highest frequency contained in an analog signal xa is maximum x xa is if maximum is equal to b, if the maximum frequency is b, capital B, then the signal is sampled at a rate fs which is greater than 2 of f maximum or 2b. Then xa can be exactly recovered from its sample values using the interpolation function. So this is the interpolation function. Gt is equal to 2 sine 2 pi bt divided by 2 pi bt. Here B is the maximum frequency of the analog signal. Now, thus XATB may be expressed as this equation here, where XAT is equal to summation of n is equal to minus infinity to infinity XA of n by Fs G of t minus n by Fs. Now, where XA n by Fs is equal to Xa and t is equivalent to Xn. So this is our discrete time signal. Now, when the sampling of a Xat is performed at the minimum sampling rate Fs equals to 2b, the reconstruction formula become like this. So Xat is equal to summation of Xa n by 2b into sine 2 pi b t minus n by 2b divided by 2 pi b t minus n by 2b. So the sampling rate Fn is equal to 2b or 2f maximum is called the Nyquist rate. So I have discussed about this in the earlier slide. So the upcoming figure will illustrate the ideal digital to analog conversion process using the interpolation function. So this is the ideal digital to analog conversion. So this interpolation theorem or interpolation method is being used in the receiving end. So from these samples, number of samples, the receiver will try to reconstruct the exact analog signal or the exact message signal which has been transmitted from the transmitter. Now, let's do an example using the Nyquist theorem. So consider we have an analog signal and the equation for the analog signal is like this. Now, what is the Nyquist rate for this signal? So the frequencies present in the signal above are, so we can say that here this terms represents 2 pi f1t. So 2 pi f1t is equal to 50 pi t. So pi t is neutralized. So 2f1 is equal to 50. So f1 is equal to 25. Similarly, f2 is equal to 300 divided by 2, which means 150 hertz. F3 here, 100 divided by 2, which means 50 hertz. So the maximum frequency component is F2 is equal to 150 hertz. So our sampling frequency should be twice of this maximum frequency component, which means Fs should be 300 hertz. Now, Nyquist rate is equal to 2 into F maximum. So Nyquist rate or Nyquist frequency is equal to 300 hertz. Now consider an analog signal Xat is equal to 3 cos 2000 pi t and 5 sin 6000 pi t and 10 cos 12,000 pi t. Now, this is the problem which is exactly similar to this one. So you have to practice this problem at your home by yourself. Now, the quantization of continuous signal. The process of converting a discrete time continuous amplitude signal into a a digital signal by expressing each sample value by a finite number of digits is called quantization. The error introduced in representing the continuous value signal by a finite set of discrete value levels is quantization error or quantization noise. We have discussed about quantization noise in our previous lecture briefly. Now, this is the a graphical representation of the quantization process. So in case of this is the analog signal. So we are from the analog signal, first we will get this discrete signal. Then from the discrete signals, the amplitude axis is discretized into some fixed levels. So we have to take these values, these random values, into that particular levels. Say, for example, I have a level in 1 and I have a level in 0. Now my discrete time signal has an amplitude between 0 to 1 and it is actually 0.8. So if the value is greater than we have to consider, we have to imagine a midline between 0 to 1, which is at 0.5. So if the amplitude of the discrete signal lies above 0.5, then we will consider that value as 1. And if this value lies below 0.5, then we will consider that value as 0. So this is how quantization process is done here. Now the coding. So if we have L number of quantization levels, then we will have 2 to the power n, n number of bits to represent each sample. So this is the end of our lecture.